I like it. All right, so today we're doing motion problems, and it's a little bit different. Now that we know how to solve systems, we can set these up a little bit simpler than what we had to do at the beginning of the year. We don't have to work so hard because we've learned more. Okay, so remember that our basic form for motion problems is that R times T equals D. What's the R stand for here? Rate. Good. T is time and D is distance. Okay, perfect. So again, we solve these using one variable way back in chapter 3. But they're often easier to solve using two variables. We just didn't know how to do that then. So it's going to put some more tools in your toolbox. Okay? So we can use a system of equations. And I'm hoping that you're like, oh, this is so much easier. Okay. So two cars start toward each other at the same time from towns 612 miles apart. And they pass in 6 hours. Or they meet, right? One travels 2 miles per hour faster than the other. How fast is each car traveling? All right, so let's think about this. We've got two cars at different towns. So we're going to have a town over here and a town over here. And we know, how far apart are these towns exactly? 612 miles. All right, 612 miles. All right. So we know that they, one is traveling, are they traveling away from each other or towards each other? If they're going to pass. Toward. Okay, so one is going this way and one is coming this way. Yes, in chapter 3, but we weren't able to use systems. That's why we're going through it today. Because now we can set them up a little differently. Okay. Do we know anything about these two cars?
One's going faster.
One's going faster. Okay, so we have a faster car and a slower car.
My guess is he's going 75.
Do what?
Oh, my guess.
Your guess is how much?
75.
Oh, that's pretty close. Okay, so we've got a faster car and a slower car. All right.
It's 65.
Not quite. So when we fill out the rate this time, like when we fill out our chart, last time remember we had to work all through because one car was going faster and one car was going slower, and we had to write each one in relationship to the same one. We had to use the same variable. Now we don't have to use the same variable because we know how to solve a system. So we could say, all right, well, the faster car is going its rate, the rate of the fast car, and then for its time was how long? 6 hours. Okay, and so what was its distance? Okay, 6f. We always put the coefficient first. Okay, because remember, it's just the rate times the time equals the distance. So its rate was, or its distance was 6f. Okay. Yeah, right. So what's the rate of the slow car?
Slowness.
It's slow. We can put an S. It's the slow car. How long did it travel for?
6 hours.
6 hours. And so what's its distance? 6s. And you're like,
I would be going fast.
how does this help? Right? Like, okay, so we're able to use two variables. So now we have to process through what those are. Okay, so how are we going to get two equations out of this? We need a system that relates them all together. How do we do that? Like 6f times 6 equals 6f?
Sure.
That won't, I would say, that won't help us. We need an equation that has both of the variables in them.
Well, don't we do that one? Rate times time equals distance?
Well, that's what we did. Rate times time equals distance to get here.
But we haven't put it together. Equals 612.
We did put them together. Right, I'm saying, so how do we put them together?
Well, we have to do f times 6,
Oh, I know. And then we would have equals 6f, and we'd have to figure out what our f equals. Right?
But we can't. Okay, so we're just going to get 6 times f equals 6f. So then you're just stuck with 6f equals 6f. It's not Not really helpful there. Okay, so we did all this work here to get the end, like, so let's think about this for a second. In our picture, I know you got it, just a second. So this is our distance. This says, hey, the distance we traveled is 6F and 6S. So if we go back to our picture, right, this is a picture of the distance. So the fast car traveled how far?
Oh, I think I.
What's the,
Wait, Venus, no, but- Ouch. Is it Sorry, I don't know the answer to what you just asked, but do you do like 6F plus 6S equals 612?
yes. Because like we drew this picture and said, well, this is what the fast car did and this is how far the slow car went. But we actually know the distance.
Olivia said that earlier.
She did, yes, but I want you all to understand why we can get there. So I'm trying to explain how we can figure out to put them together. So the distance that the fast car traveled is actually 6F, because it's the time that it traveled times its rate. And the distance that the slow car traveled is 6S, which Bailey and Olivia have both pointed out is equal to 612. So our first equation is 6F plus 6S equals 612. So the distance the fast car traveled plus the distance the slow car traveled equals 612 miles. Great. That's not it, because it's a system. We have to have a second equation in order to solve these. So it does go back to relating, like, how do the F and the S relate? What's their relationship? Because we got two different variables.
Well, F is equal to S plus 2.
Okay, because the faster car is 2 miles faster. So the fast car is equal to the speed of the slow car plus another 2 miles. That is two equations and therefore a system. How would you solve this system? Would you use? You would substitute, absolutely. Why?
Because
F
equals S plus 2.
You already have the F equal to S plus 2, so you're going to substitute it in for F. Perfect. So this is going to be 6 times
S plus 2
the quantity S plus 2
plus 6S
plus 6S
is equal to 612.
is equal to 612. All right, Chase, what do I do next?
You want to distribute, so it'd be 6S, there's no negative, plus 12, plus 6S equals 612.
Awesome, great. Okay, Cheyenne, what would I do next? Yeah, we would combine the like terms. So the 6S plus a 6S.
12S.
Okay, so 12S plus 12 equals 612. All right, Bailey. Malin, what's your turn? What would we do next?
Minus 12.
Minus 12, perfect. So 12S equals 600. All right. Let me get somebody else. Cameron. What would you do next?
Divide the 12 by 600.
Okay. Divide by 12. So S equals 50. All right, so the slow car is going 50 miles an hour. 75 wasn't terrible. And then you dropped it to 65. It was better than saying like 8. So how fast is each car traveling? How are we going to find out?
The car is going 50. The fast car is going 52.
How do you know that?
Because it says it's 2 miles per hour faster than the other.
It's 2 miles per hour faster, and also we can plug S in just like we do, right? We substitute 50 back in like if we wanted. So F equals the 50 plus 2, so F equals 52. And you can put MPH for miles per hour, or you could put miles with the per sign and then HR.
I don't.
Mhm.
Why? Okay, that's not really all that much faster than 50 miles an hour.
What?
52 is like only 2 miles plus. It's only 2 miles faster than 50.
Yeah.
Why not just go like 65?
Because the problem said they only went 2 miles faster.
Well, that's weird.
Maybe the speed limit was 50, and so one person drove 50, and the other was like, I'll go a little over, but not too much because I don't want to get pulled over. That's what I would say. But we knew it from the beginning it was only 2 miles faster. So, but yeah, so one went 50 and one went 52.
Or the speed limit is 55 and they're both slow.
This is true. That would not be me, but that's possible. Okay, so at the bottom, yeah, I hit the wrong button. Okay, at the bottom of your paper, we're going to talk about something entirely new that we did not talk about last time. It's talking about wind current, or wind and water currents. Okay, because we get some totally weird problems that are harder to deal with when we use current. All right, so when we travel into a headwind or upstream, it's going against the current, so it decreases your rate of travel. So headwind and upstream decrease. Awesome. So if we look at these, when we have a headwind, we have the rate minus 20. Well, it's not always minus 25. So I circled the wrong thing here. We always have the rate minus whatever our wind is. In this case, it's 25 miles per hour. And in the upstream, it's the same. It's the rate minus, because they're always decreasing, so they're always subtraction. When we're using a tailwind or downstream, okay, that increases the rate. So we have the rate plus for both of those. Because our next two examples both deal with these things. Okay, so figuring out how do we write the equation with those. Okay, so headwind upstream decreases. So like if you think of headwind, it's at the front and you're driving into it. It's going to slow you down if you're driving into the wind, right? If you're going upstream, that one hopefully you all are probably more familiar with. Anybody who've ever been canoeing, right? You always float downstream because. Okay, well, even better. So would you ever want to have to go upstream in whitewater rafting? Yeah, right? Wouldn't that be terrible? Because we usually float downstream, like when we're floating.
5 straight days and slept in a tent on rocks. It was probably.
That sounds like fun.
Let's say.
Oh, it was, but a tree fell down on this little kid.
Oh, that's not so fun.
Did you like get hurt?
No, Cameron, that didn't get hurt.
Okay, so let's look at the back then. Example 2. When his Sunday school class went canoeing, Brent paddled 12 miles. So he paddled 12 miles down the river in 3 hours. After paddling back upstream for 2 hours, he had traveled 4 miles.
The kid is like really strong.
Yeah, right?
Overachiever.
So how fast does Brent paddle in still water, and what is the rate of the current?
No.
We don't.
Oh.
We don't know.
I remember when.
He kissed his
Okay, so these are the conversations that we're having problems with because I'm teaching and you're having all the side conversations. Okay? You do much better when you focus during the lesson and you talk when you have some time to work on homework or something. Okay? All right. So, from what's on the other side, what do we know about Brent paddled 12 miles down the river in 3 hours? Was he going upstream or downstream? If he's downstream, okay. So if we're going downstream, is that the rate plus or the rate minus? The rate plus. Okay, so we're going to have, in this case, the rate that he's paddling. Let me change colors here because this goes to the red. Actually, we'll keep all of them kind of color-coded. So the rate that he's paddling plus the current, because it doesn't say what our current is in this case. And how long did he do this for? 3 hours. 3 hours. Good. So what's our distance?
12 miles.
Yes, we do know. 12 miles. Nice catch, Cameron. Right? It was 12 miles. Good. Now, if we look at upstream, right? He paddled back upstream for 2 hours. What is upstream? Is that the rate plus or the rate minus? The rate minus. Okay, so this is going to be his rate of paddling minus the current.
2 hours.
He traveled for 2 hours.
And then 4 miles.
And his distance is 4 miles. Perfect. Okay. Now, this one is a little bit different when it comes to writing our equation to solve the system. Because we're supposed to do the rate times the time to equal our distance. And we don't have a relationship between our distance, right? Before, where they met equaled the 612. We don't have that. So how are we going to write what equations are going to come out of this one?
R plus C times 3 equals 12.
Yeah.
Could cancel a C.
So we're going to get there. Okay, R plus C is a quantity, so we put parentheses around it, times 3 equals 12. And then what's our other equation then?
R minus C.
It's the quantity R minus C times 2 equals 4. This time the equations are there because we're using two different variables in each one. So that equation itself is 1 for the system. Okay, so there's a couple different ways you can go about solving these. You can cancel the C's. Okay.
Aren't we supposed to?
So
You would have
how would you do that? Because we have distribution as well happening.
you would.
So you're right. It's nice that you see this though. Like, wait, if I can keep them in this form, the C's will cancel. But you see you have this, do you see what I'm saying? You have 3 that you're supposed to distribute. So how can you get around distributing that? We can divide it out, right? We can go ahead and divide by 3 on both sides. I wrote one line. And then I would have, this would become R plus C equals, what's 12 divided? 4. Okay, what would I do on this one when I'm distributing, have to distribute a 2? I could divide by 2. Yeah, okay, so we can, like when you see that, we can work around that a little bit. R minus C equals 2. All right, now we can add them together because these do cancel, so we're left with R plus R is not R.
R equals 3.
2R.
2R, there you go. 2R equals 6.
R equals 3.
Divide by 2.
Negative 3.
R equals 3.
3 miles an hour.
Okay, so yeah, this would be excellent. 3 miles an hour if we add that in there. So MPH.
Is that the answer?
Well, that's one of the answers. We need to plug it back in, right? Because it asks us, how fast does Brent paddle in still water? So that's his rate. What is the rate of the current? That's going to be the C, because we put them both under rate. So R is Brent's rate. You could have used B if you would have rather, right? Brent's rate, you could have used a B plus the current, either way. So yeah, we got to plug it back in. So which one do we want to plug it into?
Top one.
The top one? All right, so we're going to have 3 plus C times 3 equals 12. Well, do we just want to go ahead and divide by 3 again so we don't have to distribute? So if that's the case, couldn't we have just plugged it in that one? Or that one? Yeah, we could have. Oh, and I put R instead of 3. My apologies here.
I don't want
Subtract 3.
Subtract 3.
C equals 1.
C equals 1 mile per hour. So we would say Brent's rate is 3 miles per hour and the current is 1 mile per hour. The next one's going to be a little bit harder because we're talking about nautical miles. Does anybody know anything about nautical miles per hour? Anybody?
It's like a mile in the ocean. It's
It's a
different. It's not like it's like being nautical mile. It's not the same length as like a mile.
right
On
on land.
or something.
Yes. Okay. So it is a nautical mile per hour. But like we say miles per hour, instead of saying nautical mile per hour, there's a shortcut. Does anybody know what that is? No. You would think it might be NPH. It is a knot. Yes. Like when you hear, if you ever watch any shows where they're on ships or whatever, or they're on a boat and they're like, okay, let's speed up to 25 knots, or let's slow down to 17 knots. That's what it is. It's nautical miles per hour. So that's why I said the next one might be, it's going to be a little bit harder because we're not as familiar with knots because we live on land, not in water. And we're not a big boating community necessarily.
I'm a boater.
Well, see, then you should know about knots. That's why I said, does anybody know about knots, like nautical miles?
Hang out. Oh, well, I don't
Okay.
drive the boat. I just kind of sit there.
Okay, see, there you go.
I'm
All right,
there for the
so
famous help.
1 knot, K-N-O-T, equals 1 nautical mile per hour.
I know about knots from a video game where you are a pirate.
Okay, there you go. There you go. All right. So now here's the other thing. Nautical miles are not just for at sea. They're also for planes. Okay, they fly nautical miles as well. So when flying the 1,900 nautical miles to California, James flew nonstop for 4 hours. Flying home by the same route and under the same weather conditions, the flight took 3 hours, 30 minutes. So what rate would the airplane have flown with no wind, and what was the wind speed? So it's kind of telling you lots of information there.
I'm confused because if they drove home at the same speed, wouldn't it have been just 4 hours?
You mean the weather conditions?
Weather.
Okay, so they flew home with the same weather conditions, but there was, I mean, like that's, I would agree, like that's misleading, but there is wind.
To California, they were flying into the wind,
Mm-hmm.
and then on the way back, they were flying with the wind.
Right. So we're talking on the way there, they had headwind. On the way home, they had tailwind.
I understand now.
Good. Okay. All right. So that's going to help us. That conversation is going to help us with our flight to California. So remember, in our flight to California, they're flying, it took them longer. So are they flying into a tailwind, or are they flying with a headwind? Headwind. So is that plus or minus? Minus. Okay. So instead of using R and C or whatever, how about we use P for plane? Are we okay with that? And then minus W for the wind.
Why is it minus W? Because it's taking them longer.
Because it's taking them longer. So they're flying into the headwind, right? Like if we looked at the beginning, if it's a headwind, we're flying into it, it's going to slow us down. Does that make sense?
Yeah, that makes sense.
Okay. So yeah.
The rate's decreasing.
Right, because the rate is decreasing. All right, do we know how much time he flew for?
4 hours.
Okay, 4 hours. And do we know the distance?
100 and,
We
yeah,
don't.
it's the very beginning. 1,000.
Oh, wait.
1,900. Okay, good. So now we're ready for the flight home. Okay, it took him 3 hours and 30 minutes. So is he flying into the headwind, or is he flying with the tailwind? With the tailwind, because he's going faster, right? So he's flying faster. It's the same weather conditions, but this time he's flying in, or flying with the wind instead of into it. So this is what? What's our rate going to be this time? Not Olivia.
Plus W.
Okay, it's going to be the plane plus W. Good, Josie. All right, what's the time here?
3 hours and 30 minutes.
Okay, how would we write that in there?
3 hours.
3.5.
3.5. So 3.5 or 3 1/2. I'm going to go with 3.5. And what distance did they travel to get home?
1,900.
It's the same thing, 1,900. So if you wanted a picture, if you thought a picture would be helpful, like we drew on the front one, we could do that. Does anybody want a picture, or are you guys pretty good? Okay. All right.
I want a picture.
All right.
No, I'm okay.
Okay. Okay. So what equations would come out of this?
T minus W times 4 equals 9.
Yeah,
Okay.
it would be the same thing, but quotation marks are, or not quotation
And then
marks.
P
Parentheses, good. So P minus W times 4 equals 1900.
The second one would be P plus W times 3.5 equals 1900.
All right. Good. So those are our two equations in the system.
And then you distribute. No. You
Divide by
divide it. Divide by 4.
You want to divide by 4? Okay.
And then divide by 3.5.
So then this one's going to be P minus, well, actually, let me write it over here because then I could line them up a little easier. P minus W equals
475.
475. Thank you, Connor. You are on it.
That's Cameron.
Thank you. Sorry. That's what I meant. Thank you, Cameron. You are on it. Okay, divide by 3.5, we said.
Then P plus W equals.
Well, I told all of you you should have your calculator out.
542.85.
Okay, so 542. Did you round appropriately?
No, it
Should
should be 86.
be 86? Okay, thank you. I was like, always make sure you round when you're taking it, and to the thousandth place is great. All right. So then now what? When you combine the, or
Get rid of the W.
we can get rid of the W.
Then P.
2P.
2P, yeah.
Okay.
Equals, and then add 475.
Okay, Connor, you don't get to answer anymore. 475 plus 542.86.
1017.
1017.
Or it could be
1017.86.
I think it's easier to not round to a 9 because we're going to be dividing it by 2.
No, I said take it to 2 decimals.
Oh, no,
Always.
because Olivia's saying you can round it to 1017.9.
Right, but that would be one place value. That'd only be the tenths place.
And it'd be an odd place value. So
Well, so you should always round to the hundredths place if you're going to round. So then I heard somebody say divide by 2. So P equals 508.93. Do you guys know, like, once you do this, once you round, you should actually change your equal sign to an approximate sign?
Wouldn't it be 2P?
It would not, because we divided by 2 here, so the 2's canceled. So, one small detail. But okay, so then we have the plane is going at 508.93. So that's kind of our intermediate answer. We can knots. What do we do now?
P, let's do the bottom one. P plus W times 3.5 equals, well, 508.
Wait, you're saying?
No, it would be 508.92.
No, I don't think
Okay, so I think I thought maybe you started to use this one. Was that what you're doing? You're plugging this into this one? Okay. So because we've already done this work and got here. And then P, yes. So I just wrote it down like he was saying it because we're using this one. So then P is,
508.92.
okay, plus W equals 542.86. So then what do we do?
Subtract 508.93.
it's going to be like 20 something.
33.07.
33.07. Okay.
33.07.
Okay. Got confirmation on that. All right. So, we could, and like at this point, you could round it. Okay. The plane, how fast is the plane going?
509.
Okay. So the plane is 509 what? Knots, because it's nautical miles. So knots means nautical miles per hour. Otherwise, you have to write nautical miles per hour. Okay. And what's the wind?
33.
30, there you go, 33 knots. Very nice. You got it. And so on the front, you only have 1 through 9 odd, and then 19, 21, and 23.
Generous.
Well, they take a little bit. So.
Yeah, that is fairly long.
So